Hi, thank you for the introduction. So this is the topic of my PhD. How do I switch slides with this? Right, this is my disclosure, so let's jump straight into it. So what is FFR and why do we want to predict it? When it comes to coronary artery disease, FFR is a really well-established index, which is simply the pressure ratio between the pressure measured straight after the stenosis and the pressure measured before the stenosis. And if that index is less than a certain threshold, then it is deemed that the stenosis is severe and needs to be treated. This is usually measured invasively using a catheter. So what hasn't been really well established is the use of that index in other vulnerable vessels, such as the iliac arteries or the femoral arteries, which is the motivation behind my project. And to add to that, using CFD is the main tool that I'm using to non-invasively measure that pressure. And CFD in combination with 4D MRI, I believe will produce good results for that. So how this is done, it starts with the MRI imaging set. The geometry is segmented and then meshed, and after that CFD can be run on the mesh. In my case, I'm using STAR CCM Plus for Newtonian fluid simulations, and I'm measuring pressures at various locations in the model, as well as outlet mass flow rate. It's worth pointing out that the accuracy of CFD simulations is very, among other things, very heavily dependent on the boundary conditions. So therefore, I'm going to present a few cases with a few different types of boundary conditions that I've used to see which one produces the most accurate result. And we start with the mass flow rate. So first of all, this is a steady state case. The inlet is a mass flow rate inlet where the data has been derived from 4D flow MRI. And then for the outlet, we have either pressure or resistance type boundary condition. The pressure meaning you prescribe a certain pressure that you're looking for, and the solver keeps that constant in this case. Whereas the resistance prescribes a pressure that is based on the mass flow rate through each outlet. And for each one of those, I have two variations. We have two different resistances. We have the DCP condition, which is different pressure at the two outlets, and then we have the ECP conditions, which is equal pressure at the two outlets. And here on the left, first of all, we can see what the mass flow split results look like. It's really obvious that the ECP and resistance boundary conditions do predict that there's more flow going out of the healthy vessel as compared to the DCP condition, which shows us that, according to that, there is more flow going out of the stenosed vessel, which is not very realistic. In terms of what the pressure looks like, so just a reminder, we have 5 different points, so 2 of them are in the aorta, and then we have points 3, 4, and 5 in each iliac artery. So we can see how the pressure develops. How the pressure develops in the model. So for the resistance and for the DCP condition, we can see that there is a big pressure drop where the stenosis is, and that is maintained throughout the vessel, while in the ECP condition, we only see a small pressure drop, and then the pressure is recovered to be equal in the athletes, which is what the boundary condition dictates. How this translates to FFR and actual measurement of pressure drop. So here on the bottom, we have the pressure drop magnitude compared to in vivo measured data from literature for similar kind of stenosis. The group for the stenosis that was measured in this study was with stenosis between 76 to 92% area reduction, I think. The model I'm working with has 78% area reduction. So we can see that the DCP condition best matches that pressure drop, followed by the resistance, and then finally the ECP condition tends to underestimate that pressure drop, which is also reflected in the FFR values, which are quite high for the ECP case, and drop down for the DCP and the resistance cases. If we want to translate that into, if we want to translate that into pulsatile case, the equivalent of prescribing constant pressure would be to prescribe a waveform at the outlet. The resistance boundary condition essentially remains the same, since that is dynamically calculated by taking the mass flow rate, and then an extension to the resistance is the first order system, which is the two-element twin castle model. We can see in this case that for the prescribed waveform, we get quite an unrealistic pressure drop, which is actually larger in the diastolic phase, while in the resistance boundary condition case, we do have a higher pressure drop in the systolic case, but then the pressure remains more or less the same throughout the simulation, and there's also no phase shift between the two pressures at the two locations, while in the two-element twin castle model, we see the pressure drop, and we also can see a phase shift. And in addition to that, actually, the range of pressure is more realistic than the range of pressure that we get from the other two boundary conditions. Following on to that, to further validate the mass flow rate, because that's important for the resistance boundary condition, another set of simulations was performed using same methods on a different model, this one with less severe stenosis. And we can see here the results for the mass flow spread. In this case, the reference is 4D flow MRI. And once again, we can see that the resistance boundary condition is the best at predicting what the flow split is, while the DCP condition actually produces a ridiculous backflow, which is not realistic at all. So to conclude, we've got the pressure and FFR, which is well represented by the DCP and resistance type boundary condition. However, the mass flow split is only well represented by the resistance boundary condition. And in addition to that, for pulsatile cases, we've got resistance and two-element twin castle model producing a realistic pressure drop. However, the two-element twin castle model actually produces a more realistic phase shift and more realistic pressure range overall in the model, while the prescribed waveform produces very unrealistic results. So what are the next steps in this project? One of them is to do large AD simulation approach to further see the effects of turbulence on the results, and also investigate the behavior of non-Newtonian fluid, because this could be significant in that kind of geometry, and also use fluid structure interactions to take into account the deformability of the vessel wall, and last but not least, validate that that data with experimental results, and also expand the study to more patients, because at the moment it is fairly limited in terms of only having a few geometries to work with. And that's it. Thank you very much for the attention.